started. So welcome everybody to the last session of the day. Welcome everyone to the last session of the day. Today we have Sean Sinclair, who's a fifth-year student at Cornell, representing his advisor, Christina. So Sean is going to basically talk about some themes that synthesize some of the themes from yesterday about regret and some of the themes from today about reinforcement learning. So Sean, take it away.
Thank you so much, Steve, for the introduction. So yeah, like you said, my name is Sean Sinclair. I'm a grad student at Cornell in the Operations Research Department, advised by Christina, who unfortunately could not make it today, and also Sid Banerjee as well. And so today I'll be talking about online reinforcement learning and the regret formulation. And what I think is nice about this is today we talked about reinforcement learning. Yesterday we saw bandits and the regret formulation. And so today this presentation will be kind of synthesizing these two discussions that we've had thus far. The presentation will be mostly at a high level. I'll discuss some ideas of the proof, some intuition and how the algorithms are developed. But I'm here all semester, so if you have questions about the specifics for some of these proofs, I'm happy to talk about them then. So to start us off, kind of the main question that we've been discussing today is, given a Markov decision process, how can we find the optimal policy? And I put given here in quotations because we saw kind of two different settings of what this quote unquote given means to the algorithm. One setting that we saw this morning during Buena's presentation, I called a fully known model. And this encapsulates the setting where the primitives of the MDP, the rewards and the transitions are known in advance. And the question that people try and answer, yes, this morning we saw algorithms like value iteration and policy iteration. But the question is, how can you understand the computational complexity of solving these problems when the state and the action space start to grow? And so a very good example of this is a stochastic queuing network where every piece of information about the system, the arrival rates, the service rates, if you know these upfront, you know the rewards and you know the transitions of the MDP. So you're in this kind of fully known model. But the issue with a queuing system is that the state space is unbounded. And so obviously using these tabular algorithms that work for a finite state space a priori do not apply to this setting. And so researchers have studied extensions to some of the techniques that we discussed earlier today with value iteration and policy iteration, adding some levels of function approximation as well on top of this in order to learn control policies in this fully known setting. Okay, so that was kind of the first hour of today's discussion was in this fully known model. The next model that researchers typically consider, I like to think of it as a generative model assumption. And this is related to Srikant's presentations that we just saw. And I'll make that connections clear in a second. And so in this model, the primitives of the MDP, the transitions in the reward function, they're not known in advance. But what the algorithm is able to do is sample an arbitrary state and action pair to observe the next reward and the transition, a sample of the transition distribution for the next state. And I know that Srikant kind of formulated this by saying you have a trace from some given policy that's handed to you, but there's this extra condition on that d-min factor, which in order to properly address it, you somehow need to be able to explore arbitrarily across the system in order for that term to be bounded in these settings. And similar to the previous two presentations we saw, the main question that people try and address is to understand the sample complexity for finding a good policy. So we discussed these finite time bounds of understanding how many samples, how long this trajectory needs to be in order to learn a good control policy in this setting. And an example that kind of fits into this particular model is potentially like a physics simulator, where maybe you don't know all of the interactions of the system, but you have a simulator that's good enough that you're able to use to execute this step here, where you can feed in the simulator a state and an action and observe a transition in the reward for the next step. Okay. And earlier today, we saw algorithms designed for this setting like Q-learning and TD learning, and some extensions with function approximation that were applied specifically under this generative model problem setup. Now, I think kind of the main motivation today is trying to answer, do we actually need another setting to reason about learning control policies in a Markov decision process? And so a lot of problems have restricted interaction with the environment that is not captured in these two different problems. Like with the fully known model, potentially a priori, we don't actually know what the rewards and the transitions are of the process, which means algorithms designed under this setting, you can't use them. The second is with this generative model where potentially you're not able to sample kind of arbitrarily along the system in order to evaluate the next step transition, but instead you have kind of a restricted interaction structure. And so an example that really highlights this particular kind of deficit that we saw with the last two models is with a drug dosage example. And so here we have a very cartoon model of a little person along with some schedule that we're trying to decide of a sequence of drug dosages that we're going to give them over the next 3 days. And so the way that the system works is you observe some health outcomes about this patient. And for the first day, you decide to prescribe them 5 milligrams of some random medication. You prescribe them this medication, you observe some information, some new health outcomes, and you decide on the decision for the next day. Let's say it's potentially 15 milligrams. Again, you observe some health outcomes and decide a final dosage for the medication, which we decide to decrease back to 5. Okay. And so in this specific problem, what we had to do first was decide on the policy that we're going to execute for this particular patient. So we decided on these decisions, we executed it, and we observed some data about this particular policy that we can then use to update our policy. And taking this particular example and putting it back into the previous two problem setups, in order for this drug dosage model to fit in this fully known model setting, it would mean that you needed to know the entire interaction structure of the problem upfront. You would need to be able to say, I know for every given patient, for every health outcome, and every drug dosage decision, what is going to happen at the next day, which obviously doesn't make sense. So fully known model does not particularly apply. And the second model with the generative model, what that is saying is that we can simulate what would have happened for any dosage decision. So we could say we could take an arbitrary patient. Let's say we want to sample from some particular like health outcomes. That would mean that we had access to a patient with that health outcome. We could prescribe them that medication and observe what happened next, which also doesn't particularly fit into this problem setup. And so the issues with these two models motivated what I like to call the kind of quote unquote online model. And this is different for a couple different reasons. So the first reason is that you can only sample trajectories under a chosen policy. So first you have to pick a policy, you're stuck with that policy, you observe a trajectory under that policy, and based off of that data that you observe, you're able to change the policy for the next round. So these policy decisions are kind of made up front. And the theoretical question that people try and address is try and analyze the regret that's incurred over time when you're comparing the policy that you're playing against the optimal policy in hindsight. And to some extent, you can think of this as being the kind of quote unquote most complex for two reasons. One is that exploration is constrained. So similar to Shrikant's discussion earlier, potentially there's a state action pair that the behavior policy doesn't reach. And so what would you do then? That needs to be addressed in this model because we're trying to learn the optimal policy. And the other issue is that typically the estimates that you get of all of these different rewards and trying to estimate the value functions, they quickly become correlated across time because you're using different policies potentially in order to collect more data. And a good example that I like to think that kind of fits into this model is a memory management. Yeah.
Say anything about the regret if I didn't know the optimal policy. And to know the optimal policy, I have to do all these things that you told me I can't do.
Yeah, so later on, I'll talk about how you can get a guarantee in terms of regret and turn it into one that looks like sample complexity. So you get kind of guaranteed convergence. But yeah, that's a good point. Regret, as it's written down, you cannot calculate it, but we like it because it gives you the sample complexity bound.
I see. So I shouldn't think of I have occurred so far this, but I did not make that my next decision. That's not what you're trying to tell us.
Yeah. So once we start seeing how the algorithms are designed, they are somehow independent of the definition of the regret. We're just using the data we've observed. Yeah. And so a good example of this is with a memory management model, where typically you try and use policies that are designed in this online model setup for a couple reasons. And one of them is because there's very complicated demand dynamics that somehow make using this online model where your policy is shifting over time useful in practice. And I think some of this discussion will also be done tomorrow during the next day of the bootcamp. So I want to pause here, ask if we have any questions about the 3 different model setups. Great. Okay. So previously, so far, unfortunately, I guess I missed the memo. We have been discussing MDPs in what's called the infinite horizon discounted setting. Everything that I'm going to be talking about today is specialized to what's called the finite horizon setting, which is a little bit different. So I want to briefly kind of outline what the differences are and how we can relate it to some of the discussion that we've seen so far. So similarly to what we've seen, an MDP is defined in terms of these primitives. So we have the state, the action space, same thing that we had from before. The difference is that we have a reward and a transition distribution, but now they're indexed by a step. And that's so that we can allow the reward function and the transition distribution to change over the course of an episode. And so, for example, potentially in the drug dosage model, the reward that we get on day 1 looks different from the reward that we get on day 2. So we add this additional dependence on the current step. And this last variable H is called the time horizon, and that's the number of decisions that you're trying to make. And so previously in the example with the drug dosage model, we decided 3 decisions for the drug dosages for the 3 different days. And so the horizon, capital H, is going to be equal to 3 for this particular problem. Okay. And the last bit is this bit on the bottom, where now previously we only had to look at stationary policies, so policies that did not depend on the time step. But intuitively, you can think, because the reward and the transitions also depend on the time step, the policies that you consider should also depend on the time step here. So our policies have this additional dependence on the time step that we've listed at the bottom. Okay. So this is the main difference between this and the models that we discussed earlier, is instead of a discount factor that's included, we have a finite time horizon after which the problem is finished. We make the 3 dosage decisions and the policies are no longer non-stationary. Yeah. Yeah, so the time could be part of the state space and then you can eliminate this, but then it just so happens that policies have to be step dependent even under that setting. And so the reward and the transitions not depending on the step is not super important. But because of the finite horizon, the policy has to depend on the current time step. And I guess you could think of a good example for this is you could consider some maze where you're given 50 moves. So what you would do first is go to the goal location and then just go left, right, left, right, left, right, left, right, continue to accumulate that reward from the goal state. And so the policy that we have to consider has to be indexed by the time step. Yeah. And there is a relationship between this model and some of the models that we discussed earlier. For example, typically you can take this time horizon. Here it is fixed and known, but if you let this be a geometric random variable with parameter gamma, then it turns into the same problem that we saw before. And because the geometric distribution is memoryless, the policies are now not step dependent, but somehow not important for the discussion that we'll be doing today. Okay. And so with this, I wanted to flash the Bellman equations here I've also written them over on the side here because we'll be referring to them a lot. And just to point out the two differences from what we saw previously. So just like policies are now indexed by time, the Q function and the value function also have to be indexed by the time step H. Okay. And previously, we defined the Q function in terms of reward plus gamma times the expected value function. But now, because all of these are additionally indexed by the time step, we have the Q function for a time step is the immediate reward plus no discount factor here, the value function at the next time step. Okay, so everything here now is also indexed by time steps. And so you're relating these Q functions at one time step to these Q and these V functions for the next time step. But again, all of this could be related to the infinite horizon discounted setting similarly too. Okay. Do we have any questions about Bellman equations, MDP problems, stuff like that? Great. So I kind of sketched before what this online model was. I said, one aspect is you're only able to sample trajectories under the currently chosen policy and use that in order to update the policy for the next round. And again, the question that people try and tackle is to look at the regret, which is incurred over time when you're comparing the value of the policy you play versus the value of the optimal policy. And again, I want to emphasize that the transitions and the reward distribution is not known to the decision maker. And so the way that the interaction structure works is over what's called a sequence of episodes. First, what you have to do is pick a policy. In the drug dosage model, that was the policy that we are picking for this particular patient. So we picked it up front. That is the policy that we're going to play for this particular episode. We then take that policy and execute it in the system over the H steps that governs the finite time horizon of the MDP. Once we've executed it, we are able to collect some data set. Similar to the presentation from Shrikant, the data set that we observe is a sequence of state, action, and reward pairs. But now there's a finite time horizon. And so we observe H of those pairs, where H is the time horizon of the model. And with this interaction structure, just want to kind of reiterate, now we have these two parameters that we really care about. One of the parameters is H, which is the number of decisions that we're making over time. In the drug dosage model, we had 3 days. So our H was 3 for the 3 days of decisions that we have to make. And we have this additional parameter K, which for this drug model, you can think of it as the number of patients that we're kind of running this experiment on, going one by one, changing our policy over time. And so H and K are kind of related to each other, and also similar to the discussion that we had yesterday, where K you can think of as T in the multi-arm bandit problem setup. It's the number of decisions that we're making, where each decision, our H is equal to 1, because we're only making a one-step decision and observing a one-step reward. And lastly, our goal, the theoretical quantity that we try and analyze is regret. So regret is defined in terms of the total number of episodes, where you sum up over each episode, looking at the value of the optimal policy and subtracting off the value for the policy that you played for that particular episode. Okay. And similarly to what we had discussed with the multi-arm bandit problem set up yesterday, initially the regret would scale linearly with respect to K. That's if you were not learning anything at all. And so the goal is to show a sublinear regret guarantee for the algorithms that you're proposing. And just to kind of take this and relate it back to the question from before, you can show that if you have some type of sublinear regret guarantee, all of this is wrong up to constants that I just didn't put in. But if you have a regret guarantee, scaling in terms of some way, let's say it scales in terms of square root of k, you can take that guarantee and swap it into a sample complexity guarantee, where you also get in terms of the number of samples required to learn an epsilon optimal policy, which scales in terms of the regret guarantee that you had here. So if alpha is 1/2, then the number of samples is 1 over epsilon squared. Okay. So we have, yeah.
Do you have constraints on the kind of policies you can choose?
Yeah. So you can choose, for the time being, you can just pretend that we're considering in the finite state action space setting. So you can consider any arbitrary policy from the state space to the action space.
So you don't have, because you're motivated by like some policies are kind of crazy in the medical setting, but you don't have that here.
Yeah. So later on, actually, we'll discuss about potentially restricting the space of policies that you consider. But for the time being, you can kind of consider arbitrary ones. Yeah. Do you also?
Strawman solution, would it be reasonable to just discretize the space of all policies and then just use one of the algorithms in the edge case?
Yeah, so that's a good question. So one solution you could do is consider every single policy. We know in this setting and in general that deterministic policies are optimal. And so there's a finite number of deterministic policies. But the issue is that the number of policies you would need to enumerate over scales exponentially with the number of steps, because you have to make a sequence of H decisions. So the policy space scales exponentially with respect to H, and the regret guarantees that we will get will be better than exponential. Yeah. But that is, I guess, something you can.
And it would still be sublinear in K, so at least you would get some, some sample bounds to get you started.
Yeah, that is a very good point, that when you're looking at this regret style analysis, you'll see that people will kind of assume certain things are constant and let other things scale. And that is important, because if you were to enumerate every policy, the regret would be constant if K was large enough, right? But then that constant is exponential in terms of other primitives like the horizon. Yeah, good point.
In a setting, does it make sense to set each to depend either polynomially or logarithmically on the number of states times actions?
Yeah, you can think of H as being some nice polynomial of that, but later on when we discuss regret bounds, I'll briefly mention that people look at ways that you could pay exponentially in terms of some components in order to get better dependence in terms of other components. Yeah.
But should I think of H as given or something that I can tune? Because isn't an episode something that's like naturally occurring?
Yeah. Yes. So you can think of the horizon H as something that's known and finite and not big. Yeah. Okay. So something that we've discussed a little bit briefly in the presentation so far, but I want to kind of emphasize in a little bit of a different way, because it forms the fundamental for a lot of different RL algorithms that we've discussed so far. And so this kind of fact that we need to do is to be able to compare two policies, okay? And we'll see later on how this becomes important for picking different particular policies that you're comparing. But for the time being, let's say you have some reference policy. That's the one that you're currently using, okay? And then you have some other policy, which will denote pi alg, and that's the policy that you're trying to kind of optimize over or pick for the next episode, okay? And you want a way to be able to compare their performance. And so suppose you're at some state and you notice that the two policies are proposing a different action. The reference policy is proposing to go down, the algorithm's policy wants to go up, okay? And what you're trying to understand is, okay, we know the two policies, they differ on this action. And so how much do you have to compensate, quote unquote, in order to compare the performance at this particular step of these two different policies? Okay. Now, if we're just looking at one step, what you could do is look at the immediate rewards. So the reward that the pi alg is going to get is the reward for being in this state where the action is dictated by the algorithm's policy. That's how much you get immediately from going up. Okay. And then if you go down, you follow the reference policy. The reward you get is the reward for being in the state following the action by the reference policy. And so a natural thing to kind of write down as a compensation is just this difference. Okay, the difference of the reward that we get for going down versus the reward that we get for going up. Okay, I haven't really done anything yet. I just wrote down rewards, right? And I subtracted them. Okay, but for this, we can look back onto our Bellman equations. Here I wrote down the optimality ones, but the ones for a particular policy look similar, where the max is replaced with the action taken by the policy. And with this equation, we can subtract off the value function for one of the policies in order to transform it, that exact same difference, to be equal to this term right here. And for some intuition behind it, what this right-hand side term is doing is it's just looking at the value for playing the decisions made by this new algorithm that, or this new policy that you're proposing, pi_alg. And on the left-hand side, we have the Q function, which from before we saw was what is the immediate reward we get for taking the reference policy. So that's the one-step reward that we saw from before. But then we switch into this new policy pi_alg. Okay. And this term is important enough that people in the RL community have defined it something new called the advantage function, which is just defined to be this exact difference right here. It's the difference of the Q function and the V function, where here pi_alg, you're writing the policy you're taking for all of the subsequent steps. And here for pi_ref, you're indicating the action that you're taking right now. And they call this particular thing the advantage function. Now, the signs on this quantity are crazy. Okay, it's really hard to think about. And so, for example, ignore what pi_ref is. We don't really care what we're doing now. What we want to do is find the optimal policy. Let's suppose somehow we're able to guess what the optimal policy is. And so pi_alg is actually the optimal policy. Okay. Then here we're looking at Q star of S for some action and subtracting off with V star of the state. And so the advantage function for the optimal policy will be negative, meaning that if we switch to pi_alg, we're able to improve our rewards, which is somehow counterintuitive because of the negative, but we'll see kind of where it comes out in a second. Okay, so I'll stop here, ask if we have any questions, but I just want this kind of comparison to stay in the back of your brain because we'll be using it a couple times when we talk about designing algorithms. Yeah.
If I follow the optimal policy for one step and then follow it for the rest of it.
So the difference is if you plug in pi star here, you're telling the optimal policy, oh, you want to play some action? Don't do it. Play some other action.
Oh, I see. So pi_ref is not, okay, got it. Okay.
And so if pi_alg and pi_ref are both the optimal, then it's 0, right? But pi_ref is what we're currently using, and we're just kind of supposing for now that it is not optimal. Yeah. Great. So we're now ready to start the discussion about algorithms. Earlier, in this kind of fully known model setting, we discussed two different approaches for designing algorithms. One of them was called value iteration, and the other was called policy iteration. And we remember when we actually executed these steps, these one-step update procedures, we very heavily relied on this fact because we were evaluating the Q function for a given policy, which you can only do if you know the transitions and rewards. And when we were doing policy improvement, we were plugging in this transition distribution. So a priori, these two algorithms, to some extent, they don't initially work. But similar to Srikant's discussion, for the online model, we've developed algorithms that fall under both of these buckets that are called value-based and policy-based approaches. And for the first part of the presentation, I'll be briefly discussing some of these policy-based approaches just to highlight some things that are missed so far. And then the rest of the presentation will be focused on the value-based approaches, where we'll discuss the algorithms more concretely, discuss the regret guarantees that you're able to achieve, and so on. And so we're going to start off with these policy-based algorithms. Now, something that was kind of alluded to earlier was you have to, like, if you're running a policy-based algorithm, you have to actually like pick the policies that you're going to be optimizing over. So Shrikant kind of proposed this particular form of policies that are defined in terms of this known feature representation. And earlier we had this question of like, are you considering every policy or you're considering some restricted class? An example that I like, that I think particularly highlights this is with inventory control, particularly the news vendor model. The way that this model works is you are some kind of newspaper salesman, let's say, and you have some current inventory of newspapers that you have on hand. Each day, some demand comes that are buying some of the newspapers, and you have to decide how much you want to order for the next time period. And people in the operations research community have studied this problem extensively and come up with a particular parameterization for these policies called base stock policies. And the way that base stock policies work is if your inventory level is below what's called the base stock level, you order up so that your inventory for the next time step is equal to that level. But if your inventory is above the level, you don't order anything. And you can kind of write as a picture this particular choice of policy like this, where you have the inventory level on one axis, the policy on the other, where if your inventory is 0, you order up to the base stock level. If your inventory is equal to the base stock level, you don't order anything. And above it, you also do not order anything. And this policy here is parameterized by one variable, S, that we can think of as parameterizing the policies that we're going to consider in the MDP. And so typically when you kind of take this RL formulation and write it in terms of optimization, you can think of this particular parameter S as this theta, this parameter for the problem, for the policy that you're optimizing over. And so these policy-based algorithms try and solve this particular problem instead, where you're trying to maximize the value of the parameterized policy in some space of possible policies, where theta could be S, characterizing the base stock policy that you're optimizing over, or any other parameterization. Do you have a question? Okay, great. And so this a priori, it's kind of weird to see the dependence on theta. It's somewhat non-obvious. And so what people typically do is they just rewrite the value function and just write it as some function j that's only a function of theta. Okay. And here, when we write the problem in this way, we have an optimization problem. Okay, there's some objective function. Okay, we can't really evaluate it. We'll address that in a second. But there is an objective function that we can write down, find in terms of a parameter that we can also write down, and write it in this way. And with this, it's somewhat clear that you can use existing optimization algorithms applied to this, like gradient descent. And I put in emphasis the fact that it needs to be stochastic, which we'll see why the algorithms you should use need to be stochastic. And that's because you can evaluate J of theta, but we'll talk about ways that you're able to kind of estimate it from data. And so this has been done across a variety of different optimization style algorithms with zeroth order or gradient-free optimization algorithms, gradient-based or also Hessian-based optimization algorithms. Okay, but remember from before, I said we have this objective function that we cannot evaluate because we do not know the model. Okay, and so intuitively, you can think of all of these algorithms. They really don't depend on what the objective function is. They depend on your ability to do comparisons. And so a primitive to all of these optimization style approaches is how can you compare the value of two policies? And you can think of this as just doing kind of grid search for the threshold level for the base stock policies. Potentially we cannot evaluate this, but if we're able to evaluate the difference in the performance of two base stock policies, we're okay, because we can do kind of standard kind of grid search procedures. And this is also readily witnessed if you're doing 0th order optimization, where you take your current parameter, evaluate policies in a grid. You only care about the differences because we only care about one-step improvement. And by being able to do a comparison, you're okay to take one step of the algorithm. And so as a primitive, essentially all we need to be able to do is compare value of two policies. And so looping back to our discussion from before, previously we looked at comparing two policies, your current policy pi-ref, some new policy you're optimizing over pi-alg, looking at just one step's difference of rewards. But our objective is a value function. So in order to look at the difference of the value functions, you can just take this quantity, you can take this one step difference and sum it up over the trajectories. And so this principle here of looking at a one-step compensation and summing it up over the trajectories gets to probably what is one of the most famous results in reinforcement learning called the policy difference lemma. And what the policy difference lemma looks like is looking at the performance of two policies. So the value for one policy subtracted with the value from some other policy. In order to evaluate the difference of these two policies, you take an expectation over trajectories from one of the policies, your current policy, your reference policy, of this advantage function on the right-hand side of the proposed policy, this new policy pi out. Okay. And so this kind of relationship of this one-step compensation, taking an expectation over the trajectories, allows you to recover this policy difference lemma. Okay. Now, this is useful for a multitude of reasons. One reason that's useful is, okay, if you had perfect information, you can evaluate this quantity exactly in order to guarantee one-step improvement. So with perfect information, you can do grid search to be able to compare performance of policies, to be able to take one step and improve your policy at the next iteration. Okay, but we don't have perfect information. We can't evaluate these quantities exactly. And so what's nice about this, and I won't go into the details, is you're able to evaluate this using Monte Carlo rollouts under your current policy, where the way that you're able to evaluate at a high level is taking trajectories sampled according to this reference policy, doing importance weighting in some way in order to evaluate the advantage function, and combining those two facts together to get an estimate for this quantity. Yeah.
Here, the dependency on the density of the different states for the out is hidden in A.
Yeah. So when you're actually doing the Monte Carlo estimates and evaluating the performance of these policy-based algorithms, you have terms that look like this. And so typically when I said you could use any optimization algorithms, somehow not true. And so in practice, what people do is they take optimization algorithms and modify them in a little so that you're only taking small steps so that the variance that you'll get that's hidden here isn't super bad. And that's to some extent one of the biggest downsides of policy-based algorithms is you're introducing additional variance by doing this importance sampling, but in practice, it works super well. Okay, so this difference that we took, you could use it as kind of a primitive in order to do 0th order optimization. I'm not going to go into the details, but the other optimization approach you could do is a gradient-based optimization algorithm. And so we need to be able to take a gradient of this objective, which by taking that analysis that we had before to be able to compare two policies, somehow a finite difference, take the limit in order to get the gradient. And you get what's called the policy gradient theorem, which is maybe one of the second most celebrated results for RL. I guess the order potentially is debated. What's the first, what's the second? But the way the policy gradient theorem works is you have an expectation under some policy. This advantage function we saw before, again, but taking the derivative of the current policies, the log probabilities under the current policy. Again, what's nice about this, you can evaluate it under Monte Carlo estimates of the current policy that you're trying to evaluate the gradient under. And so these two terms, the policy gradient and the policy difference lemma, with some modifications to the optimization algorithms, allows you to use existing techniques from optimization and apply it to RL, where we have the primitives to be able to do the comparisons because we can't evaluate the subjective exactly, and use our standard optimization algorithms from there.
So are these out or no regret, or are you just trying to find the best?
Yeah, so the regret guarantees for this style of algorithms is more recent. I mostly wanted to put it in here. For the most part, the regret guarantees look at the generative model setting, but I wanted to put it in here because it had not been discussed yet so far. And I think that really understanding regret guarantees of this style approach is something that could be looked at in the future. Yeah, good question. Okay, yeah.
Do we know something about the conversion speed of these Monte Carlo algorithms?
Yeah, so people have studied the convergence guarantees of Monte Carlo rollouts of this and plugged that into convergence guarantees of the optimization style approaches. I can't recall off the top what the exact form guarantees look like, but some of the papers that are listed here look into that. Okay, yeah.
So just so that I am not completely losing you. So basically, you're trying to figure out the optimal theta for this thing.
Yes.
You're using this in the gradient steps.
Yeah.
This is basically like a stochastic gradient.
Perfect. Yeah. So that, to some extent, really helps us. What we're going to think about next is, okay, we're using, and in practice, people use gradient-based or zeroth order optimization algorithms, and they ignore what the subjective function looks like, this J of theta. Like potentially it's non-convex, potentially it's non-smooth, but you just apply and hope for the best. And in practice, these algorithms really work well. Okay, but there's also been growing theory behind these two that I want to talk briefly about, just to kind of highlight two papers in the space. So the first one, to some extent, mentioned briefly by Shipra yesterday, is to first consider a restricted class of policies. So I am in an OR department, and one of the things that I really enjoy that people in OR do is they study fundamental models and come up with policies that are provably near optimal in this specific setting. And so going back to inventory control, one of the reasons that we like base stock policies is people in the OR community have studied them extensively and shown that they're provably near optimal. You can increase the scale of the problem. You can add complexities to the underlying inventory control model, but this simple base stock policy still works very well. And so once you restrict your class of policies, this J of theta is not some random J of theta. It's now the J of a particular base stock level. And so in this paper, they exploit additional structural properties about the value function for particular parameterized policies. For example, potentially this particular value function is strongly convex, which means we're able to get optimization guarantees, and we can evaluate potentially it exactly over traces. Like the estimation problem suddenly becomes much simpler. And so this is one way that you can think about using this on a particular application is study the application in theory, come up with a restricted set of policies that work well, use gradient-based optimization procedures on that restricted class. The second approach that I also really enjoy and wanted to mention is a paper by Dan Russo, which for those of you who are not participants, in the fall of 2020, the COVID year, there was a theory of reinforcement learning program at Simons, and there was a presentation by him at one of the boot camps on this particular paper. So if you're interested, I would heavily recommend watching it. And what this approach does is it characterizes conditions under which this particular objective as a function of theta doesn't have any local maxima. So you know if you're doing a gradient-based optimization procedure, you are okay, because every optima is a global one. And the two assumptions are quite nice. The first one is kind of natural. You need some additional differentiability and some continuity assumptions on this J of theta, relatively standard and makes sense what it's required for. The second one, I think, is particularly beautiful. And the requirement is that the policy space is closed under what's called these policy iteration steps. So if you take a policy, do one-step policy improvement, the new policy is also in the policy class. And in the paper, they discuss about a particular application with LQR, somehow makes sense with the reward function. And by maximizing a linear function, you are able to recover the LQR policy again. Makes sense. Something somewhat interested in queuing theory that I've personally looked at is under specific settings with stochastic queuing networks, you can also come up with a parameterized class of policies that satisfies this particular assumption so that you can use gradient-based optimization guarantees and provably converge to the optimal policy. Yeah. 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 So that's not enough. Was the question in this application whether it contains the optimal policy, or does this assumption imply closure under the optimal policy?
Like a general assumption.
Yeah, so you need this plus extra stuff. You need this closure assumption too. So you know the optimal policy satisfies it because it's a fixed point, right? But you need the parameterized set of policies you're optimizing over to also be closed in this way. Yeah.
So you need paths to go and the policies first about policy.
So with this, we have, another.
So the queuing context, state spaces, right?
Yeah.
So while you're running through your policy gradient value, what if the data you have makes the system unstable?
Yeah, so that is an additional problem that I'm ignoring when I said that this is an example that satisfies this assumption that you run into when doing it in practice. And so Chowman and Devaraj Shah have a nice paper where you somehow I think of it as like regularized by a stable policy so that you're guaranteed to stay within the space of stable policies as well. But when applying these types of algorithms for queuing networks, definitely that's something that needs to be done. And also, going back a little bit, just like we have this policy difference lemma, in the queuing literature, people have also studied approaches to look like this to be able to estimate whether the new policy you're optimizing over is also going to be stable, which can talk about offline how it fits in. Yeah. Okay, great. So with that, we are somehow concluding our discussion on the policy-based approaches and moving on to the value-based. And last minute questions before we kind of shift gears. So a lot of these value-based algorithms really are wrapped around these Bellman optimality equations, which are written as here and also on the side here for you to be able to look at as we discuss the algorithms. Says that the value for the optimal policy is a maximum of the Q function for the optimal policy. Q function for the optimal policy is immediate reward plus expectation over the state transition distribution of the value for the optimal policy under the next time step. But again, we cannot evaluate these Bellman equations because this term here, transition distribution, and this term here, the rewards are unknown. And so to address this, within the class of value-based approaches to learning control policies for regret minimization, there are two types of styles called the model-based and the model-free setting. And so the model-based, the way that it works is the two unknowns here, the reward and the transitions. Let's take our data set, we'll estimate it, take those estimates, plug them in here, estimated reward and an estimated transition, and solve these Bellman equations. Okay, you're not exactly solving the Bellman equations because you're not plugging in the actual reward and transitions, but you're approximately solving them. You take those estimates, play the action that's greedy with respect to those estimates, which makes sense. And what's important about these policies is the time complexity and the space complexity. It scales as h s squared a. which arises from maintaining an estimate of this transition distribution, which has an H dependence, an S and an A dependence, and another S dependence for the output of the transition distribution. So that's the time and the storage complexity for the model-based algorithms. Okay. The model-free algorithms, so related to Srikanth's presentation from earlier, like we didn't really see, it was discussed how this could work, but we didn't see these model-based algorithms specifically. We mostly focused on model-free algorithms that estimate this Q function directly by applying this like Bellman optimality operator. You again play greedy with respect to those estimates, and the time and the storage complexity is better because you're not storing an estimate of this exactly. And so it's only HSA for the size of this 3 tensor indexed by steps, states, and actions. And so the rest of the presentation will briefly describe these two algorithms, talk about the regret guarantees, and some open questions that lie within the space. Okay, so a beautiful paper which outlines some of the regret analysis under these style of value-based algorithms formulates it like this, that I want to briefly kind of sketch. And it's very much related to the same optimism principle that we saw yesterday for the bandit literature. And so the way that a lot of these value-based algorithms work is, let's suppose you're in some arbitrary state at some arbitrary step, and you have 3 different actions. These orange lines here are the actual optimal Q function, okay, that's unknown. And so because this one is the largest, we know that the optimal policy plays action A1, okay? And the way that the algorithm works is initially you estimate the Q function to be its maximum possible value, which if you say the reward is bounded by 1, the maximum possible value for the Q function is the number of time steps remaining for the horizon, which is capital H minus little h, where little h is this current step that you're considering. Okay, so that's these greenish lines that we have on the top. And so initially, we said our algorithm was playing greedy with respect to the estimates. So we're somehow going to randomize among these 3 different actions. Let's say we pick the 2nd and the 3rd action, okay? And we get some new data and we somehow update our estimates. We'll talk later how we actually update the estimates, but for now we just update them, okay? Now, notice that our estimates are still above the true value. So we maintain optimism, but A1 is now the one that we're going to play because we play greedy with respect to the estimates. So we play A1, update our estimates in some way. Oh, we saw now they're about the same. So we play randomly again and continue like that. Okay. And what happens after a while is for some of the actions, we're able to rule them out, just like the bandit setting, and converge on the optimal action being A1. And so this paper formalizes a way that you can get, design, and analyze the regret guarantees for this style of value-based approaches. And also want to emphasize that similar to the bandit setting, you'll notice that the estimates converge to the true value. Previously, it was for the optimal action. Now it's a little bit more complicated. The estimates converge to the true value for the optimal actions on sample paths under the optimal policy. So it looks a little bit different, but when you run these algorithms in practice, you'll start to see pictures like this, where if the optimal policy, if it visits this state, you'll see that the estimates converge for the optimal action and the other ones don't. And so the paper that I have listed at the bottom shows kind of 3 invariants that a value-based algorithm should satisfy in order to be able to analyze its regret guarantee. The first invariant is that you're maintaining estimates of the Q function. They should be optimistic, which means that with high probability, they're larger than the true Q value that is unknown. similar to the multi-arm bandit settings, where we maintain estimates for the mean reward that were with high probability upper bounds on the actual mean reward. The second property that we do, these estimates should be somehow non-increasing, and they need to decrease quote unquote fast enough, which you can think of saying that they decrease at a rate of 1/√t, where t is the number of times you have been in this step, played in this state, playing this action. Okay. And the third property is just that you have estimates for the Q function. The policy that you play should be greedy with respect to these estimates. And using these three principles, you're able to come up with a regret guarantee that's very general, that allows you to analyze essentially an arbitrary value-based algorithm that satisfies these three different assumptions. I'll also highlight later that this paper does some additional stuff too, but for now can just say you get a regret guarantee for algorithms that look like this. So going back to the two style of algorithms, the model-based and the model-free, we'll start off with the model-based algorithm. So the way the algorithm works is you're at some episode, you have a data set you've observed so far, the state, action, next state, reward, tuples. Yeah. Yeah, so this result, you can take parts of it and use it to analyze an arbitrary value-based policy that satisfies these three different assumptions. They propose a policy and analyze that one. You can take their same analysis. It's somehow general enough. Take their same analysis to analyze arbitrary algorithms. And so in a second, I'll talk about how people have used this style of framework to analyze model-free, model-based, other styles too. Yeah. Okay. So for the value-based algorithms, start of the episode, you have a data set. Take your data set, estimate the reward and the transition distribution with an empirical estimate. We're in the tabular, the discrete setting, so empirical is okay for now. Okay. Estimate the reward and transitions. Then you just take those estimates. You have the Bellman optimality equations here. Plug them in for the unknown reward and the unknown transitions. And so the way that the estimates are obtained are by solving this dynamic program where you put in an estimated reward and transition function into it. So just like the Bellman optimality equations, the estimate for the value function is the maximum of the estimate of the Q function. The estimate of the Q function is the reward, but we plugged in the estimate. An expectation, but we plugged in an estimate of the value function. But again, we plugged in an estimate. Okay, so it's essentially take all of the terms for the Bellman optimality equations and put a bar on top of it. And the policy that you play is, again, greedy with respect to the estimates of the Q function to follow into that optimistic style of algorithm from before. And you'll notice I have one additional term here, which is the exploration term, just like we saw with the UCB style of algorithms, that scales as some kind of polylogarithmic constant that I put here as lambda times 1/√t, where t is the number of times you're in that state taking that action. And what I think is so beautiful about all of these approaches is a priori, it's kind of unclear how to do exploration in an MDP. Like the dynamics are complicated, right? So you would think that you would need to change or modify. Yeah. Oh, so this lambda is polylogarithmic with respect to S, A, K, and a high probability factor. Yeah. And so what I think is super nice about this style of approach is it turns out that the most simplest thing you could do, just add on a standard exploration term, allows you to explore enough in order to get a regret guarantee. And so just to be able to directly contrast the estimates for the Q function and the true from solving the value iteration, again, unknown reward and transitions, plug in an estimate, and add on some additional bonus term here in order to incentivize exploration. And in order to relate this to the discussion from yesterday, you can think of an MDP when the horizon is equal to 1 as a bandit, because you're just making one decision. That's it. You don't care about the future value. So this term is nothing, it's 0. And so your estimate for the reward is the empirical plus a bonus term. And so it turns out that you're able to take this model-based algorithm, and if you apply it to a bandit, it exactly reduces to the same UCB algorithm that we saw yesterday, where our estimates for the mean reward is the reward plus this exploration term, and the arm that we play is the one that maximizes this. Yeah.
So just to clarify, the T here is the number of times I've seen this state action pair?
Yeah. Yeah.
And not the longer.
No, yeah. And taking this style of approach and relating it back to these 3 invariants that the algorithms need to do, we have the bottom one for free because the policy we pick is playing greedy with respect to the estimates. The top one, we added on a term that scales as 1 over square root of t. You can use standard concentration inequalities to say that's the deviation. And so by adding it on, you're able to show this expression here. And with a little bit of algebra, you're also able to show the second expression here. And so with this, you are able to get a regret guarantee for this particular style of algorithm that looks like this. So the algorithm that I showed here is presented in this paper here, and it's been modified, tweaked slightly in later works in order to improve the regret slightly to get this, but can talk about that after. And so the regret guarantee for this algorithm, first it scales square root of k. So we're sublinear with respect to the number of episodes, which is good. We're able to take it and obtain a sample complexity guarantee. We're polynomial with respect to the horizon and square root with respect to the number of states and actions. And in a min-max setting, people have constructed min-max lower bounds to show that this has the optimal dependence on the number of episodes. It has to scale in a worst case with respect to the square root of k. But it is a model-based algorithm. And so its time and space complexity is worse because you're estimating the transition distribution, which takes more memory, it takes more time in order to execute. And this last dependence on H is still kind of current research. People have worked on trying to shave factors on H here, but pay in terms of S and A and other ways. And just to emphasize again, this regret guarantee is worst case. We saw in the bandit literature that we were actually able to improve on square root of t. We were able to get logarithmic in t. And just like the regret guarantee that we saw before, we got square root of k. And later I'll talk about recent work that has been able to get this log k dependence instead. And again, these regret guarantees, they're very much worst case. They're not capturing particular problem structure that you see. And then also I wanted to briefly say that we added these kind of arbitrary exploration terms that look like lambda over square root of t. People, when they actually implement RL algorithms in practice, they do not do that. What they do is just called epsilon exploration, where with some probability epsilon, you sample an action randomly. It just for the theoretical guarantees, you need to do the bonus-based exploration. Yeah.
Is that because epsilon greedies actually perform better in practice?
Yeah, so it's because it performs better in practice. And in order to, if you run experiments of these kind of discrete tabular settings, randomly sample an MDP and compare epsilon greedy versus the optimal choice of the bonus term lambda, so you additionally tune that constant lambda, you see that epsilon exploration most times also works better. Yeah. Okay. Yeah.
I'm trying to compare the generative model to this online model. There's a way of reducing this model to generative model. Yes. If I put in time as part of the state, and then restarting every H period, that's part of how I encode the state.
Yeah, so even if you encoded the time step in the state information, the model is still fundamentally different from a generative model, because given an arbitrary state, you need to, in order to obtain information about it, you need to design a policy or use a policy that gets to that state. Whereas in a generative model, you just say, oh, this is the state I care about. Go to the simulator and sample a transition part. Yeah. Okay. So that was the model-based approach, and next up is the model-free approach. Again, the key difference is that instead of estimating the rewards and transitions, we're estimating the Q function directly. We play greedy with respect to the estimates, and there's better time and storage complexity because it's only HSA instead of HS squared A. And for this, Shrikant did an amazing job earlier presenting the Q learning algorithm. And so the model-free algorithm for the regret minimization standpoint is Q learning with one modification where you add on this exploration term. Okay, so instead of having this kind of D min parameter that we saw before, in order to get the regret guarantees, we deal with that by adding on this exploration here to our estimates of the Q function, where again, we're estimating this Q function along a sample path under the current policy. Our estimates are updated in terms of a linear combination of the old estimate plus the other form of the learning rate parameter times a one-step reward plus estimated value plus this exploration term. What's interesting about this is that the original paper showing the regret guarantee for this model-free algorithm has a particular choice of learning rates that is required in order to get the analysis to work. And so that learning rate that you need to do depends on the horizon H, and it looks like H plus 1 over H plus T. And this is needed to some extent in order to initially get, it still satisfies the normal like learning rate optimization guarantees, where if you sum it over T, it is infinite, and if you sum it squared, it is finite. So we still satisfy the normal like Robbins-Monroe condition, but this dependence on the horizon enforces that the learning rate favors kind of more later updates. And intuitively, I like to think about it as one issue of these model-free algorithms is the way information is propagated backwards across steps. In the model-based algorithm, you are solving the full Bellman equations. And so if you learn something new on the last time step, that information will get propagated all the way back to the first time step. Whereas with these model-free algorithms, it gets done a little bit slower because you're only updating one estimate of the Q function on a sample path. And so with this, we have a regret guarantee again. We have the same square root of SAK term, which we wanted. So we have optimal dependence on K. But if you remember from before, the model-based algorithm had H to the 3/2. And so this model-free algorithm has H to the 5/2. There's been some work on improving on the H to the 5/2. I think they've gotten it down to H squared, which is still worse than H to the 3/2. I think that's the best result that we know so far though. And so just like the presentations that we saw before, the regret analysis for this particular algorithm has strong relations to stochastic approximation from Robbins-Monroe and Shrikant's presentation from earlier. Again, it has the optimal dependence on K in this min-max setting, better time and space complexity because you're not estimating the transition distribution. And again, this dependence on H, people have studied improving on this factor and paying for it differently in terms of the state action space dependence. And I want to kind of wrap up this discussion showing some kind of folklore comparisons of people who are implementing the difference of these model-based and model-free algorithms in practice. So I've shown two types of value-based approaches. So the most obvious question is, in practice, how can you compare the performance? And what is typically observed is that the performance of model-based algorithms is better than model-free. Definitely true in the discrete setting. Once you start adding function approximation, the answer is a little bit more unclear. But the same kind of fact is typically observed that model-based has better performance. However, the model-based algorithms have more compute because you need to somehow estimate this transition distribution, which in a parametric model is very complicated. Plug that into these Bellman equations, which for a random neural network model of the transition distribution, evaluating expectations is now also hard to do. So definitely more compute. And something that I think is interesting is to try and understand a trade-off between min-max regret and also the storage and compute requirements. This is something that's been done in bandits, where you say, if you have a bandit model, you have k arms, but you can only maintain a finite number of statistics that's smaller than k. How does the regret change in terms of the number of estimates you're allowed to maintain? Here, our model-based algorithm has more data, more compute. We see it has better regret. And is that fundamentally because it has more information, or potentially it's not? Okay, any questions about these model-based and model-free algorithms?
So model-based algorithms you described so far, you say it sounds like, this is just a high-level question. It sounds like you estimated the entire transition matrix, like, you know, SA squared by SA squared, or whatever it is.
Yeah.
Sorry, SA squared by S. What if you know that that matrix has some structure? Is there work on this that either reduces the complexity or proves better guarantees?
Yeah, so there has been a lot of follow-up work under different assumptions or models that you make on either the Q function or the reward and transitions. And typically these parametric representations that people do are one of the two. Either assume something parametric about the Q function or assume something parametric about rewards and transitions. And so in a setting when the reward and transitions are like inner products in terms of a known feature representation, there's also regret guarantees that scale square root to d square root of k, where d is the dimension of the feature representation. Yeah. And so I guess that kind of brings us to the next kind of discussion, which is all of the regret guarantees that I presented are worst case. We saw regret guarantees that scale in terms of square root of k, not logarithmic of k. And so model-based and model-free algorithms have been extended using a similar style of analysis that's presented in this paper here to get logarithmic regret guarantees for both model-based and model-free settings with slight modifications of the algorithms that you saw before. There's also been work trying to understand this kind of quote unquote variance dependence, similar to the variance dependence we saw in the bandit setting from yesterday too. And also, just like Z's question from before, there's a long list of assumptions on the Q function or the rewards and the transitions being low rank or linear or parametric under different dimension models, and come up with regret guarantees under the smorgasbord of dimensional assumptions you can put on the underlying model. And so all of this kind of discussion, I think, really relates to what we have done so far, which all of the discussion we've had today has been designing algorithms specifically for this discrete setting, with the exception of Shrikant's presentation, where we optimize over these linear policies in terms of a known representation. And so even if the problem that you're actually applying it to is tabular, like let's say you want to code it up, you need to make an estimate of the Q function. You go to NumPy, you tell it to make the estimate, and you turn into something that looks like this, where suddenly you can't even store an estimate of the Q function within your memory. And so this, I think, leads to what is most summarized as the current research for reinforcement learning, is trying to design algorithms that scale. And in order to do this, I think that there's two main assumptions that people do. One is apply function approximation to the underlying problem. The second is additional modeling assumptions on the underlying problem. And this is something that I've also worked in, and a lot of the people in the room in, and I think is something that we should also be discussing this semester as well, on how different modeling and function approximation settings could be incorporated in reinforcement learning. So with that, I will stop here, ask if we have any questions before wrapping up.
I think we can take one quick question and then the rest offline.
Yeah.
So you talked about optimal dependence on K. Do we have lower bounds in this sentence?
The slide with a reference on it. So this paper here shows lower bounds with respect to K. There's because of the, okay, I will tell you after as far as our in 2017, but there is a paper that shows fundamental lower bounds with respect to K, but fundamental lower bounds with respect to these other parameters, the S and the A and the H dependence is still ongoing. People have been able to shade factors like the shade H, no dependence on H, but pay exponentially in S and A. And people have done achievability guarantees, so you can achieve it, but there hasn't been a min-max setting for the rest of the parameters. Yeah.
Wait, doesn't the K1 follow from bandits?
The K1 follows from bandits. You get H square root of K from a sequence of bandits, but yeah.
All right, I think we'll take the rest offline. So thanks everyone again for coming to another great day of tutorials. We'll continue tomorrow, meeting at 9, starting at 9:30, and we'll start with Anupam's talks on competitive analysis.